All right. Good morning, good afternoon, good evening, everyone. I'm Charles Gale, and I'm happy to be chairing the first session of this 2022 edition of the JETSCAPE Summer School. An action-packed program, as you can see, and let's hit it off right away with a first speaker, Abhijit Majumdar. So Abhijit, take it away.
Hi, thank you, Charles. So yes, as Charles said, welcome to this would be our third online summer school of 2022, and so welcome to everyone. We, as for the last 2 years, we have people from all over the world joining us for this summer school. Let me just get a couple of useful information out of the way. This school meets every day for 3 hours. And it's on the East Coast of North America, that is from 9 in the morning to about noon. And of course, that translates to different times wherever you are. We have lectures, and then with what we call hands-on sessions, which is like exercises that you will do. And it'll alternate, so we'll have one lecture and then followed by a hands-on session. In every session, there's going to be a session chair. For example, Charles is the session chair right now, and there's going to be a vice chair. In this case, this is Shanshan, who will monitor the Slack channel. We would recommend that you try to attend as much of the school as possible, especially the beginning part. But of course, it's a 2-week-long program. And so you're of course open to choose the sections that are most relevant to you or for your research based on this. You're here, so you've already been to the webpage of the summer school. So right on, as you get into the web page, on the right-hand side, there are these couple of links. So first link, of course, is the timetable. That's the link to the agenda. And all the slides for each of the presentations will be available there. So if you want to look at it later after the talk. A little bit down is the software instructions. So these were already sent out like a week ago. For you to download and install the software and test it on your machine. But it's if you haven't done that, do that right away, I would say. The next and very important link is a link that says Slack channel. Okay. The school, even though the live lectures are for 3 hours every day, it's a continuous program, right? So what happens is once the lectures are over and you still have questions or you're still working on something, you can submit questions to the Slack space. You click on this, you go into the Slack channel, and then you can post a question and somebody will answer, okay, at some point. And we'll get on and give more details on that in a minute. Then, of course, there's the Zoom link, which, of course, all of you have because you're here. And there's some general guidelines we'd like everyone to follow. That's over here. So please take a look at that. Okay. Please mute your microphone if unless you've been asked by the chair to unmute and ask a question, especially to keep down any background noise. Just to save bandwidth, we'd also recommend try to keeping our camera off for as much time as possible. All of the lectures will be recorded and they will be available on our JETSCAPE YouTube channel, which will be linked on the webpage, or you could just search in Google for JETSCAPE YouTube, and that'll get you there as well. The one exception to the camera will be later today. We would like to take a group photo, which we do using a Zoom screenshot. So we'll have all your pictures. So if everybody would come on and turn on their camera, if you wish, it's up to you. There's no pressure. But if you could turn on your camera, and then we will take a screenshot of the entire of the whole school, and that will be then posted on the website or on the Slack space. Okay, asking questions. As the talk goes on, especially in Zoom talks, we recommend that you try to not use the Zoom chat. Okay, unless for some reason you've been asking questions on Slack and they've been ignored. Okay, I would recommend you go to on Slack. Every lecture will have a channel associated with it that it starts with a hash. Okay, and you go into that channel and you ask your question. Okay, and in Slack you can edit your questions. Like if you type a question and if it didn't come out right, you can go back in and you can change the question. Right, it's a live space. So and the TAs and the chairs will be monitoring that channel and try to give you real-time feedback as the lecture is going on, so that the lecturer is not deflected from from what he's doing. The questions on Zoom, like I said, sometimes might get ignored. I would only go there if your Slack questions are not getting answered, or for some reason the Slack is not working for you. Right? If you need to ask a question during the talk or during the hands-on session, please raise your Zoom hand. Right, you click on the little reaction button on Zoom and raise your hand, and then the chair will call on you at some point so you can ask your question. Right, on the Slack channel, like we said, when you go onto the Slack space, you see all of these things with the hash on them. Those are separate channels. Each corresponds to a different lecture. So for example, today's is, I don't know if you can see my mouse moving. Today's is July 25th, 26th framework. Okay, so you click on that and then you can go in there and ask, and it's basically like a texting area. So you just go in there and then ask your question. If you have general issues which are not related to any particular topic that is being covered by the school, but in general has to do with the school, I would put it in the general section. If there are problems with software installation, there's a software install channel. That's the best place to ask those questions. When you ask and you get an answer back, usually the answer will be in the form of a thread, right? So when you ask, like for example, somebody asked a question already in the software install section, and you can see down here there are 15 replies to that. Okay, and the idea is that there's a button that says reply in thread. Okay, so you click on that, and then then what happens is it does not generate a new topic. You just have a thread to the same question. And all of them will be connected together in one thread. And then if you have a different question, of course, you start a new thread, obviously. And so please keep the interactions with you within this thread, and try to not open, unless there's a new question, do not open a new thread. Yeah, as much as possible. If somebody asks a question, and you're a participant and you know the answer to the question, please go ahead and answer that, right? We strongly encourage participants to help each other, right? There will be a poll at the end of the school to choose the most helpful participants. And by that, we mean not any of the instructors. And if that number crosses, if there's enough votes, then there will also be prizes, typically Amazon gift cards for the most helpful participant. Back to the website again. So there's the suggestion box at the end. If you have any suggestions or thoughts about the school that things that you think will make it better, please go put those in there. And then there will be a survey, and this is kind of more important, right? This is something that the NSF almost kind of requires of us. So it's very important that you make sure to fill out even if you don't have any suggestions, just to do the post-school survey. And it's 10 minutes at most, 10 to 15 minutes maybe. And it'll ask you some of similar questions about how things could have been made better, and what is your general experience of the school, and things like that. Please, please, please fill out the post-school survey. Okay. With that, I want to really thank all the lecturers who have prepared all these presentations for you, the hands-on sessions, and I thank all the TAs who are here to help in real time, all the participants, and of course the chairs who take time out of their lives to come and chair these sessions. And that's all I had. Charles?
Thank you, Abhijit. Precisely on time. Great start. Okay, so the first speaker is a speaker that'll tell us about what is the framework. So Jorn Pichka from Wayne State. Jorn, can you share your slides and start?
Yeah, well, can you hear me just to make sure?
We
I can
can.
hear you.
Okay, very good. So let's share, go to full screen, and you can still see the slides and hear me?
Yes.
Okay, very good. So with this said, I also want to repeat and want to welcome everyone for joining the 2022 installment of the JETSCAPE School. So welcome again. I will give a relatively brief and let's say a 30,000 feet view introduction of the JETSCAPE framework so that hopefully over the next weeks along the hands-on session and the different physics aspects you will be walked through, and you will be encouraged to implement if you choose to do this, that hopefully it will put it a little bit more into context why certain implementations are required. I also want to repeat, in order to organize our thread a little bit, that if you have issues with installing or running JETSCAPE in Docker, running here refers to the kind of first test, not anything later on which will happen in the hands-on session. Please use the appropriate Slack channel, as Abhijit already discussed, so that we don't mix up software installation issues with other questions you might have. And if you have other questions concerning this lecture and the hands-on session, please use the appropriate Slack channel, which is July 25th to 26th framework. Okay, so with this, let's move on and introduce the whole JETSCAPE project, so to speak. And there are basically two main parts to the JETSCAPE collaboration and project. So one is the actual framework, which is the basis for the event generator. So where you put in the physics and really create your events. So this is the topic for today, but over the course of the school, another important aspect in order to basically get more precise and indeed with the Bayesian analysis and Gaussian process emulator really become more quantitative in terms of the relevant physics parameters. There is a statistical toolkit which can and should run in tandem or after you have created events. So this is not what we will discuss today, but if you look at the timetable, you will see that at a later stage this will be discussed indeed. So besides being an event generator in a sense that there will be physics modules provided, in principle the JETSCAPE is a general purpose Monte Carlo framework. So it's not only for jets. So you will see that some of the setup of the design is indeed inspired by our question of jet quenching, but it is flexible enough to be considered a general purpose event generator. And we will come back to this when we discuss about the future of JETSCAPE, that this aspect will be actually more highlighted, and also it will be reflected in the design of the JETSCAPE framework. So the most important aspect is that the JETSCAPE framework is modular. So the core framework, which hopefully you won't have to touch or check, basically decides how physics modules can interact with each other. And this you will then really look into details in the following hands-on sessions. But the modules themselves, so these are user contributed, can be user contributed. You can use the defaults which are already on GitHub. But that is the idea, that you don't have to worry about the underlying working of several aspects of heavy ion collision. So you can really focus on the physics you are interested, and you should have, at least broadly speaking, all the information at hand, which we will discuss on the next slide in terms of workflow. The second important aspect is that the physics modules are open source. So this is in principle quite a key improvement in heavy ion physics. So we really encourage that people make their physics open source so that you can have a look, and of course that predictions can be checked against many observables simultaneously, and then later on in an even more concrete approach via the statistical toolkit. With that said, it becomes very obvious that a unified framework has clear benefits, and we want to compare models of one particular part of a multi-stage evolution, because we can kind of keep everything else the same and just change one aspect of physics, which really allows us in the future to highlight the differences of different physics implementations. So this is, broadly speaking, the JETSCAPE event generator. You can find more details in our manual, and of course also on GitHub. So the main idea here is how we, at this stage in our research, think about a heavy ion collision in broad terms. And of course, this layout and the interaction between different physics aspects are indeed inspired by the jet in JETSCAPE, but we will come back to this later. So we have an initial state geometry, clearly, which influences both aspects of the hard part, so basically where the hard scattering occurred, and of course the energy density distribution will tell you how the medium itself will evolve. So we have the hard scattering based on the initial state geometry, we have an initial soft density part, then we switch to currently several implementations of hydro. We have a Cooper-Frye hadronization, and that ends up in a hadronic cascade afterburner. And for the hard scattering, we have, of course, the position and the form momentum of this outgoing parton, and then you can put actually quite a significant amount of different medium modified physics implementation. Currently, the switching between the validity of these different implementations, it's done via the via Q, via the virtuality, and you can attach all of them, and based on these criteria, you can have really a multi-stage implementation. And of course, for the jet quenching models to work, we have to you have to know the energy density at a given time and space, and so you can query the hydro to get this information, and you can also deposit energy back into the hydro, and then we hadronize, and then actually in the latest update of JETSCAPE, also the jet hadrons will enter and will be handled in the hadronic cascade. So to become a little bit more concrete, so this was very generically, but if you look at the GitHub, you see that all of these boxes have either implementations already open source on the GitHub, on the JETSCAPE GitHub repository itself, like Meta LBT Martini and ADS-CFT. We have our hadronization hybrid or colored, and is also available. Trento and other aspects of Cooper-Frye sampling and hydro implementations are optional downloads, and I refer to our installation instruction to how to get access to these additional packages. So the current status is, if you go to our JETSCAPE GitHub page, the framework is available and ready for public use for quite some time. There's a wide variety of physics available, and additions are ongoing, and hopefully after this school you will also start to contribute to this effort. Currently we are at JETSCAPE 3.5, and I would recommend using this version, but if for some other reasons, of course, you can always go back in the GitHub history and download whatever version you prefer. So what does this mean for physics comparisons? So the first physics results from out-of-the-box models from the JETSCAPE collaboration itself with certain tunes you have basically available once you download it and install JETSCAPE. However, use responsible. It's a framework, so you get the physics out you put in. If you change things, be aware that there might be a different physics implication of it. So there's already a lot of theoretical work inside, but it's of course only a slice of the overall theory landscape in heavy ions, which is quite vast and varies. And so we are really starting or continuing on the exciting phase where we have well-controlled theory comparisons via the Bayesian statistical toolkit. So you see I have a little pause button here, so I will pause now to give the chairs an opportunity to look if you have any questions what was discussed so far.
Thanks, Jörn. As mentioned, don't hesitate to post on Slack if you have any questions. If there's something you'd like to ask verbally now, you can also do it by raising your hand.
Okay, so I think it was nothing controversial and too exciting yet. So unless Charles, you found something, I would say I will continue, and frequently I will stop to allow people to catch up or ask questions.
Excellent. Go ahead, Jörn.
Okay, so what are the steps to run JETSCAPE? So you have to install and build JETSCAPE, and we will go through that. And as said, there is a separate Slack channel if you have issues with it. You have to create a configuration file in the folder config. JETSCAPE user is one of the default ones, but you can change it as you please. And you can also, for example, there's a PP tune, which has all the parameters in that XML file. So you can also load this and run it out of the gate. And there are more examples you can find in this config file. And then in principle, you just have to say execute run JETSCAPE, and you will create events. Okay, so let's go a little bit into more detail about installing JETSCAPE. So there's a very nice wiki page which on GitHub, which walks you through all the necessary steps. So there are in principle 3 ways to run JETSCAPE. One is using Docker. So this is the preferred Docker, as you might know, is a containerized environment, which basically on your computer mimics different operating system and or even can simulate different CPU architectures. If you do that, for example, if you have an Apple with an M1 chip, but you have a container which uses an underlying Intel Linux, for example, you will have quite some speed penalty, but it's still working. So that's quite a nice way. So Docker is preferred for local use, meaning on your laptop or on a desktop, and it's also the preferred way for development. If you want to, you can also use a different container environment, which is called Singularity. That one, for technical reason, high performance computing farms don't allow Docker. As question about root access, but we don't have to go into that detail. So if you want to use your container feature in large computing farms, you are basically required to use Singularity. There is a very neat conversion between Docker and Singularity, and all of these are also discussed in the JETSCAPE installation wiki. There's also the way of a manual installation where, depending on what your laptop has, you are required, or you can require all the software packages by hand and so on. So this is not recommended unless you really know what you're doing. So Docker is certainly the easiest way. And then in order to compile it or to make the executable, we use the CMake program environment in order to compile and produce executables or libraries, and they allow you to have certain options. For example, if you want to have JETSCAPE with music, free streaming and Smash or not. So you can do and decide this at compile time in your Docker environment. So Docker support, in principle, the main advantage is of course that in principle it's one line of code. You ask for the Docker environment to fetch from the Docker Hub repository the proper JETSCAPE Ubuntu version with all the software prerequisites, so you don't have to worry about this. So it's really one line in order to have this environment. And for the school, we indeed require you to use JETSCAPE via Docker, because otherwise it's quite difficult to debug and look at people's individual setup of different operating systems. So this really allows everyone in the school to have a uniform software environment and allows us to basically answer and deal with problems in a more general way. Okay, I'll stop briefly here. There are questions, comments. Of course, I want to repeat, if you have some issues, we don't want to discuss this right now, but you can use the Slack channel. So there's a question about, I see about Flex to use music ISS. I don't think they are necessarily on by default because you first have to also figure out, oh, yeah, Chun answered it, yes, they are off by default. You have to download the external package following the instructions, and then you can recompile your JETSCAPE, including these new additions. So you can do this progressively. You don't have to download everything and compile, so you can do it at any stage. But it's basically the reason behind this, that if you download the GitHub and you press compile, that everything which is in the GitHub, JETSCAPE GitHub will be by default compiled, but the external ones you have to set separately. Okay. I don't see anything else in the thread. And unless there's a hand raised, then I would say I'll continue. Okay.
Go ahead.
No, go ahead.
No, that's fine. I see no hands. Go ahead.
Okay, thanks, Charles. Now let's come to how you configure JETSCAPE, and it's done via 2 XML files. So there's a main XML file, and you shouldn't modify this. This contains default values for every possible module and parameter in these modules. So at some point in time, if of course you develop a new module, you should, and it gets included, and you make it public, and it gets included into JETSCAPE, then of course these parameters and everything what you consider the default will be in this main XML file. And you can provide a user XML file. So this allows you which of the modules you want to run and which default parameters you want to override and check for your needs. So this is actually quite convenient. So let's go through some examples here. So for example, in our main master XML file, which is in config JETSCAPE master, and you shouldn't modify this. This is basically, think about this as a database of all possible modules and parameters. So for example, if you look in here, you can of course also change the number of events, how many hydros you want to reuse, some technical settings about how much of the debug information and verbose information you want to have. What is your output format? Random number setting, which is actually consistent throughout the whole framework, so it's really reproducible. And then you have here, for example, the initial state module, and there you can change all the parameters which in that implementation of Trento, for example, are exposed for you to change. So, and you do and change this, for example, in your own user-provided XML file. So this is basically where you tailor JETSCAPE to exactly what you want to run. So you should set the number of events, the output, and then you say which of the initial state module you want to use, what hard processes, what hydro, what energy loss modules. So here, for example, in this example, you run Matter and ADS CFT, and you override values like, for example, the virtuality Q0 at which the switching between Matter and ADS CFT change, and you can change the Q hat 02, and so on and so on. And you can in principle do this for every module which is in JETSCAPE. So you can see several examples for this also in our config file. In particular, you can have a look at our PP tune, for example. I will briefly stop here in case there are questions, comments. Okay. Doesn't seem to be the case, which is sort of understandable, and all these things will make more sense once you have your hands-on session, of course. But if there are some general questions, please ask. Okay. If not, then I'll move on. So once you have defined your own JETSCAPE user XML in order to decide what particular aspects of photonic energy loss in a heavy ion environment you want to simulate and study, you have to, of course, execute it. And so there's one central executable file, which is called run JETSCAPE. If you add the modules in your user XML file, they are added automatically and accordingly to how you specify them. And the advantage is you in principle don't ever have to need to recompile this executable. So the only thing you have to do is you have to pass your user configuration file as a command line argument. If you don't do this, it will use as a default the JETSCAPE user config XML. So while this is very convenient in terms of to just use JETSCAPE as an event generator with certain setups, of course, you can, for integration in other frameworks or for different usages, you can, of course, also write your own executable files. If, for example, you want to use part of the JETSCAPE framework in a broader simulation aspect, or you want to integrate it into some other framework. And how to do this, you can find examples in GitHub under examples, under custom examples, if you desire to do so. So now coming to the output, JETSCAPE provides two default outputs. And these outputs contain the final state hadrons, the final state partons, and depending on what format, also the full parton shower history. So you have two outputs which are provided if you download the GitHub. One is our own custom-made JETSCAPE format, which is an ASCII format. So you can actually, if you don't use the GZIP version, you can look inside and see exactly what you get. And you have the options to write the parton shower history or only look at final state particles, for example, if you're not interested in the history on the partonic level. And then we provide the HepMC3 format, which is basically the standard format for most of experimental collaborations. So every detector simulation framework has the opportunity to use this HepMC3 format. So this is very convenient. And also it's compatible with the Rivet framework. Just want to mention HepMC itself has different ways of storing their information, either in an ASCII format or in a root format if you want. But generically, if you're not satisfied with either of these output formats, you can easily write your own output class. If, for example, you want to use root trees or other ways of HD5 as outputs, you can do all of this. The only thing you have to do is you have to inherit from the JETSCAPE writer base class and decide in what format you actually want to save this information. So I'll stop here. And there was a question of, is the order of the modules written in the XML order sensitive? I think it is. So you should basically follow the workflow if possible. So certainly the order, if you write your own executable, then definitely the order in which you attach the modules is important. But I think it's true in the XML too. Any other questions at this point in time? Okay, doesn't seem to be the case, then let's move on so that we can quicker end up in the hands-on session, which might be a little bit more exciting. So let's very briefly, let's give you the really 30,000 feet view of the design of the JETSCAPE framework. And it's a task-based C++ framework. So the idea here is that, as you see here in the Doxygen created inheritance tree, is that all physics modules are inheriting in one or another way from the JETSCAPE task. And these tasks get attached to the JETSCAPE framework and then get automatically executed according to basically 3 or 4 stages of any task. You have an initial initialization of that task, which gets called once, where you set all the parameters. You have an execution, which happens on an event-by-event basis, or in some special cases on a part-on case. You have a clear, which gets called after each event, and you have a finish, which gets called at the very end, if there are some things which needs to be recorded before the program stops. So that's the usual life cycle of any task. So 2 stages which get only called once, init and finish, and exit and clear get called on an event-by-event basis. There's some ways on how to alter this workflow, which I'm not go into detail, but this one can discuss it if necessary. So what is the advantage of such a task-based framework? Well, I mean, it really allows a very clear user interface and how you have to implement and integrate your physics modules into the framework. Another aspect of it is that at least at this stage of JETSCAPE and the problem of simulating photonic energy loss in a heavy ion collision, we provide you already and we define how different types of modules can interact with each other. So for example, as I said, the jet energy loss module needs access to the hydro information in order to calculate any given space-time point, what the energy density is. So currently this is provided by the framework itself, and it's implemented in what it's called a signal slot paradigm. For people who are interested in the history of it, this was first introduced and widely used by the Qt framework. But from a quick technical perspective, what is the advantage of having a signal slot? The reason is that you hide and you don't have to pass around raw pointers in order to access information. So this is basically a a safety implementation in order to make the whole framework, and also user implementation safe by actually not allowing to touch other modules unless you see here in the table the exchange of, at this point in time, very well-defined information between these modules. You can, if you please, of course, you can, since it's an open source framework, you can always add new signal slot connection if there are informations which are not foreseen at this point in time. So this is, for example, a workflow here. So in the init phase, as I already said, so you initialize all parameters for all physics modules as specified in the XML file. So you go through, here in JETSCAPE, init is just saying how many events you want and what debug output. And then you go through all the attached physics modules. At this point in time, also in this init phase, all the signal slot connections get created. So for example, here, that in this particular instance, Meta and Martini have access to the Hydra information, and of course, the necessary information from the initial state to the hard process to know where the hard process occurred. And then later on for Hydra, also the information about what the energy density is. So, and then the same idea, and you can really think about here, here you really see the task framework is, so you have your main task, you attach modules like a chain, and each module could, for example, the Jet Energy Loss Manager has subtasks, and these subtasks have subtasks, so you can build quite some recursive hierarchy. And the advantage of following this task and the life cycle and overriding the exit and clear stage is that once you adhere to this and you attach it, it will execute it accordingly and at the proper time. So you don't have to worry about that aspect at all. So, and then in the exit and clear phase, which will happen on a event by event basis, except for the jet energy loss, which is executed on a part-on basis. So basically this gets also executed recursively, and in particular the jet energy loss creates recursively a part-on shower graph, which allows generic end-to-end part-on processes. This happens for each event, and then after each event you can clear. Basically, if you occupied any additional memory, you can and should clear it up at this point in time. Of course, we encourage you to use the C++11 editions and choose smart pointers, because that makes your life also easier with respect to avoid memory leaks. So what are the data structures provided? So all the data structures, all the framework supported and provided data structures all inherit from a base class, which is called the JETSCAPE particle base. This is indeed the base class for all JETSCAPE particles. This class itself inherits privately from the FastJet pseudojet class, which basically has quite some variety of manipulation of four momentum vectors. We also added PID and rest mass and label and status, and of course also spatial information. The two derived classes from this are the hadron and the parton. Recently we also added a photon class, which inherits from a parton, which should represent a direct photon, so to speak. So, and you initialize it with the label, an ID, status code, And then you can have different constructors, but in general, you can provide and have the opportunity to provide information for momentum vector and the spatial vector, which just has space coordinates. So with this, there's one more data structure, which is called a parton shower. So JETSCAPE, we decided to store the parton shower and the evolution, which I think it's a very natural way of storing it into a graph structure. So we use the open source GTL, the graph template library, which has also additional functionalities like standard graph search and traverse algorithms if you want. And so with this, you really model the parton shower as a true graph, where the partons are the edges of the graph, and the partons split at vertices, which can and should contain spatial and time information. So this parton shower provides then several access information, like getting final partons, and also getting final partons for FastJet, which already converts it into the pseudojet, so that you don't have to worry about this by running FastJet. It also provides several other ways of querying shower information, and some of these you can find in our example of, for example, reader test. So what it of course also then allows you is to really represent this graph and basically have some nice visualization if you so desire. So I would stop here and give people time to ask about our output formats and so on and so on. Okay, so I asked some question, what is Martini and the Q and the Q naught? Well, you will actually discuss this in a little bit more detail in the relevant physics discussion. Martini is an implementation, as a particular implementation of a jet energy loss. So actually, expert Charles can say more if you so desire, or you can refer to this to later parts in our school. So here, what's the connection between hydrogeometry and geometry of the hard processes? Well, you use the same underlying energy density and Glauber or IP Glasma information about, and you can either then sample the number of binary collision profile, which gives you a probability of where in that overlap region a hard process may have occurred. And you also have the energy density information, which then goes into the hydro phase. And the hard patrons are generated. Well, this one you can decide on your own. We provide interfaces to Pythia 8, or you can just create what we refer to as a Patron gun or a Pythia gun. You can just say, I want to have a quad jet of 100 GeV at a particular location. Of course, the more realistic you want to be, the more sophisticated your hard process should be. And as said, as a default, we use Pythia 8 for that. But again, all of these questions will be, the physics question will be followed up in more detail in the relevant future days. Okay, so I think I will move on. So how do you contribute modules? And this is really what all the following hands-on sessions will be about. So for example, in today's session, you will indeed create your own jet energy loss module. So it is really, JETSCAPE is designed for users to contribute new physics modules. As you see in the task layout and in our flowchart, you can really choose and pick one physics aspect, which is represented in one of the physics modules, and you can implement and change this as you please. And you don't have to worry about all the rest of the heavy ion, right? You don't have to worry about initial state, hydro, how it hadronizes. You can really pick and choose exactly what you want and what you change. And the remainder of the heavy ion collision and simulation will be done, and you don't have to worry about. So in principle, what you have to do is you have to interface your physics, your module to JETSCAPE. And this is done by overriding the corresponding base classes of the physics modules, the appropriate standard functions of a task, like init, exit, finish, clear, in order to execute appropriately and interface with JETSCAPE. Most likely you can just from the get-go use the signal slot information to interact with other modules, unless you have some requirement of information exchange, which is not yet in. But for most parts, you basically don't even have to worry about how to get the relevant information from other modules for your physics processes. So for example, here I'll just briefly use the jet energy loss because this is what you will follow up in the next lecture. So here you see the inheritance of the JETSCAPE module base, which itself inherits from a JETSCAPE task. The appropriate implementations of Meta-Martini LBT or other jet energy loss inherit from the jet energy loss module, which is the class jet energy loss. And here we deviate a little bit from the task lifetime because the jet energy loss modules are special tasks in quotes. You don't call the execution itself, but you call a function which is called do energy loss, because we decided that we will do the energy loss calculation not on a per event level, but on a per parton level. So that's where the jet energy loss task in quote is a special task because it works and acts on a per parton level. Nonetheless, you only have to override your init function, and then you, instead of the exit function, which you should do for all other tasks, you override the do energy loss method. And the actual energy loss calculation happens in this method. And be aware that this is intended on an individual parton level. So you will see more details and discussions with, in our hands-on session later. Okay, so how do we get and set all of your module parameters, in particular if you want to add your own module and put it into, so JETSCAPE provides a singleton implementation of a JETSCAPE XML functionality. A singleton just means that this is in memory for the lifetime of the whole JETSCAPE, so you don't have to initialize, do anything. You can directly ask and query information. And it, as said, it uses by default the information in the main master file unless you override certain values in the user file. And to init parameters, you can use our functionalities like get element double, where you specify in what module you are, like here ELOS Martini, and then you can ask for a parameter X. So you don't have to keep track of the XML elements in the module itself. We made this easier by just calling the function. And similar function exists for text, integer, or more generic elements. An optional second argument in this function allows the parameter to be optional in the XML file. By default, the parameter is required to be present, or else the program will crash if it's not found. So this one you will also get more used to in the hands-on session. Nonetheless, I will still pause and see if there are some questions. Okay. So it doesn't seem to be the case, and I want to try to stay on time because I have the tendency to get on tangents. So I'll try to wrap it up in time. And we are already at the summary of the overall 30,000 feet introduction of the JETSCAPE framework. So JETSCAPE is a framework for general purpose heavy ion event generators. It's modular, it's extensible. And of course, please contribute your own modules. That's the idea behind to provide this as a tool for the community to enable well-controlled event generator comparisons, right? So for example, if there's a question about your particular medium or whatsoever in your implementation of jet energy loss, if you use the JETSCAPE framework, all of this can be standardized, and you really only have to worry about the new physics you want to implement. And it should, and from my perspective, it's a very convenient way as a testbed for theoretical and also experimental development, because you really don't have to worry about a lot of the infrastructure anymore. So JETSCAPE has been successfully used and tested in large-scale simulation efforts. And I just want to spend a little bit of time on having some comments about the last part, if people want to use it in a larger computing cluster environment. So for our Bayesian analysis, which we will discuss in the next weeks in the context of the school, we have used tens of millions of core hours running our simulations with JETSCAPE. Again, as I mentioned before, you most likely have to utilize singularity containers. Have a look at the GitHub installation instruction. Most of the HPC sites will not allow you to use Docker right away because of Docker intrinsically requires you to have root access, which of course is not what computing farms usually allow you. Good thing is you can directly convert, if you develop things in a Docker container, into a format suitable for singularity. So one of the big lessons you should, or remarks you should keep in mind is, make sure that you build your container in a reproducible way by explicitly deciding on a certain version of dependency. May it be the JETSCAPE version, the underlying physics modules. If you always do the most recent version, it might end up that actually there are some changes which change the physics, and then you lose your reproducibility. So it's smarter to just decide on a certain set. And unless there are good reasons to change this, keep it. Of course, we have simulations, and we want to save the output format, and we also might have to read in already pre-computed hydro files. These are quite large files, and you might actually run into I/O limits of the cluster itself. Usually, you don't worry too much about I/O, you usually worry more about the memory, but in our case, with shuffling around quite large files, it might actually be something you should be aware in order to minimize surprises. This also means that the output file should use the generic temporary storage of the computing rather than your home directory, because that usually has quite strict space limits, and then you immediately or as quickly as possible back this up to a permanent storage, or you just calculate observables on the fly. And one more thing, optimize for the type of simulation that you are running. So Hydro can use multi-core, Jet energy loss uses a core at a time, but can be massively parallel because it's independent. So the cores can be from any node. So be aware of what you want to simulate and choose and optimize your simulations according, or if you have a chance of choosing different environments, then choose the one which is best suited. So I'll stop here for one more second. If there are some questions. Maybe a lot of information, so maybe this is something which you can ask questions or later on if you actually try to use it on clusters. Okay, all right. And as usual, I like to do this one more thing. And this is the future and outlook, the transition or the expansion from the JETSCAPE to the JETSCAPE project. And the main difference between these, or the transition between JETSCAPE and JETSCAPE, is the extended physics scope. So we have a similar flow chart here, and at first glance they look pretty similar, and that was also good because we could use a lot of information and infrastructure from JETSCAPE. But the main key is here to provide a decentralized framework. Whereas JETSCAPE has as its core, even though it's not required, the jet evolution. So for example, in the whole JETSCAPE framework, if you may ask or wondered why we don't have any clock, for example. Well, because the time evolution is set by the parton shower itself. And in order to extend the physics scope of JETSCAPE to JETSCAPE, so any AA collision from fair to LHC energies, small systems PA, and E plus, E minus, and some aspects of EA collisions, we basically have to, of course, remove the emphasis on the parton shower evolution and go towards a more decentralized framework, and also allow more flexible exchange of more variety of information between physics modules. And I just want to very briefly show you some feature highlights of the soon to be public, hopefully, version of JETSCAPE. So first of all, the good news, it will, as far as it looks, we will maintain full backwards compatibility to JETSCAPE, meaning that everything which works in JETSCAPE will, from the get-go, with only very minor flag settings, will be working in JETSCAPE. So the main difference is here now that we do have an explicit main clock, which is attached to the main JETSCAPE task, and you can choose whatever, reference system clock, whatever time you want to have, you can use for the main clock. But we also provide module clocks, which can be attached to any JETSCAPE task. So they're not necessarily independent, they're just doing the transformation from the main clock to whatever physics time you prefer in your module. And further on, all tasks will now execute per time step. so that at each time step after your calculation is done, you can exchange all information from all tasks, which we make easier by basically allowing overall that database query approach using a query history instance, which also uses C++17 abstract data type like any and variant, so that actually you can relatively easy include non-framework data types between and as an exchange between modules. So you see these two aspects are already a big step towards basically providing a very decentralized and easy to exchange information at each time step between all modules. We have one more extension, which is relevant for heavy iron. So we allow what we call a bulk dynamics manager, which allows you to run several implementation of your bulk media at the same time. So for example, a hadronic cascade like Smash and Hydro at the same time, or whatever other implementation of the soft sector of the bulk media you want to do. So and with this, almost on time, even though I thought I would be quicker, I will finish, and I want to thank all of the JETSCAPE collaborators. And of course, we can open for questions if so desired. Thanks.
Thank you, Jörn. Any outstanding questions that are on Slack or here? Seeing none.
Okay, so then I want to reiterate what Abhijit was saying. If at any point in time you have a questions from the framework or output formats which are more general or extend beyond what you want to discuss in the individual hands-on session or other sessions, please use this channel. We will monitor it for the whole period of the school time. So if something comes up at a later stage, don't hesitate to ask and we will come back to you. Okay, so.
All right, right on time. Let's move on to Chun. Chun, you will direct the group photo taking, as I understand.
Yeah, so I would like now to ask people to open cameras. And we'll take the group photo before the break.
So whenever you're ready, Chun.
Okay, I think, okay, I will start to take group photos. So keep smiling for Okay, I think I get everybody. Yeah, thanks a lot.
Thank you. Okay, so let's take a short break and we'll resume 30 minutes after the hour. So 30 minutes after the hour. See you again for the hands-on session.
All right, bye.